Good evening. I welcome you all to the problem solving session of the NPTEL course on thermodynamics. I am Pradeev E. I am one of the TA for this course. So today I will solve the assignment problems of the week 10, and I also have some problems involving entropy and other concepts. So this is the first question. Which one of the following figures correctly depicts constant pressure curves P1 equal to constant and P2 equal to constant on TS plot for an ideal gas under normal conditions? So we know when the pressure is constant, as the entropy increases, or if the heat is added, the temperature is going to increase, right? So the slope will be always should be positive. As entropy is added, the temperature should rise up, and so that means the first option, where for P2 it is a positive slope and P1 has a negative slope, so that cannot be an answer. And for the second state, for the second option, for P1 and P2 constant lines, the line is horizontal, so that cannot be the correct. For the third, for both P1 and P2 curves, both have a positive slope, so this can be correct. And again in the fourth one, P2 has a negative slope, so this cannot be correct. So the correct option is third. For an ideal gas on a TS plot at the same temperature, which of the following is correct? Constant volume curves have higher slopes than constant pressure. Constant pressure curves have higher slopes than constant volume curves. Both constant pressure curves and constant volume curves have the same slope. So here we know at constant volume there is no work output, so when we add heat to a system at constant volume, so we have assume we have a piston cylinder arrangement, and maybe we have a stop here so that it doesn't go away of it, and now you add some heat to it, so that will increase the entropy, right, in TS plot. Started from here, state 1, and then that increased entropy, and so some heat is added, and this will increase entropy, and there is no work output, so entirely the entire heat that is given in will be used to increase the internal energy, so that will rise to a very high temperature. Whereas when we have a constant pressure process, here V equal to constant, here pressure equal to constant, so there is only a constant mass, so that will act a pressure proportionally, and some heat is added now, and now so this is 2A and this is 2B. This is A, so this will be 2A. Now if the entire heat given in will correspond to some work output plus change in internal energy, so this cannot increase the temperature as in the previous case, so it will rise to some point, something like this. So we can say the slope for constant volume, here this is V equal to constant, here to pressure equal to constant, so the slope of the constant volume case will be higher. Third question, increase in entropy principle. Heat source at 1000 Kelvin loses 2000 kilojoules of heat to a sink. Case 1, the sink temperature is 300 Kelvin, the sink temperature is 700 Kelvin. Which heat transfer process is more irreversible? So for more irreversibility, we can calculate the entropy change. So for the entropy change, we have heat transferred by T, so we can write summation of heat transferred by temperature. So for the first case, we had heat transferred of heat of 2000 kilojoules transferred at 1000 Kelvin. and heat rejected to the sink is also 2000 kilojoules, but at a sink temperature of 300 Kelvin. So this is you can say delta S1 for case 1, and similarly for case 2 it will be 2000 by 1000 minus 2000 by 700. So this is minus 6.46 kilojoule per kilogram Kelvin. No, not kilogram Kelvin, it's directly Kelvin. And here we have minus 2.657 kilojoule per Kelvin. So now we can see the entropy generation for the second case is lesser than the first case, so that means the first case is more irreversible. So now you can get an idea that if the heat transfer from high temperature body at 1000 Kelvin to a low temperature body, there will be some heat generation, and there will be some entropy generation. This entropy generation will be high if the temperature difference between the source and sink is very high. So for 1000 to 300 we had a higher entropy generation, and for the second case we had lesser entropy generation. So this will be generally written as summation over so we will have summation over this del Q by T plus entropy generation is equal to 0. So we will have S gen is equal to minus of this. So then so that is why we got minus of this. So if a heat is transferred from 1000 Kelvin body to a 900 Kelvin body, it would have been much lesser. The entropy generation would be much lesser. So here the answer is case 1. Fourth question. The increase of entropy principle states that the entropy of an isolated system during a process always increases, or in the limiting case of a irreversible process remains constant. So option is B. Fifth question, choose the correct statements. The increase of entropy principle implies that the entropy of any system cannot decrease. Entropy is never conserved. The entropy generation of a system can be negative during a process. The entropy change of a system can be negative during a process. So option 4 is right. Entropy change of a system can be negative during a process. Sixth question, for an irreversible process, which of the following is right? So when it is irreversible, the system plus surrounding, the entropy change in the system plus surrounding will be always greater than 0. Second law of efficiency. A heat engine receives heat from a source at 1200 Kelvin at a rate of 1200 kilojoule per second. So we have T1. So we have a heat engine operating between two thermal reservoirs, T1, T2. So this is at 1200 Kelvin, and this heat is 1200 kilojoule per second, or I will write it at kilowatts. And the sink temperature is 400 Kelvin. If the power output is 400 kilowatt. Now Now work reversible is efficiency reversible efficiency is 1 minus T2 by T1. So this is 1 minus 400 by 1200. This is 66.66%. Now we know the actual efficiency, that is work output by Q in, and that is 400 by 1200. This is 33.33%. Now second law efficiency is actual efficiency of the engine by theoretically possible maximum efficiency, that is the efficiency when the cycle operates in a reversible process, and that is 33.33 by 66.66, and that is 50%. So 50% is the right answer. Next problem, steam is expanding in a turbine and the process is shown in the above figure. If H ampersand H at the rate denotes the enthalpy of the steam at the point ampersand at the rate, then isentropic efficiency of the turbine is given by what? So for the isentropic efficiency, so for a turbine, the actual work output will be lesser, but the theoretical or the maximum possible work output will be more. Now, so the isentropic efficiency can be stated as actual work output by maximum work or the theoretical work or the reversible work. I will write theoretical work. And this is so for the actual work we can see it is from Z to X, so it is HZ minus HX, and for the reversible process, it is from HZ to HY, so it is HZ minus HY. You can see this option is option B. Next problem, match the following parts with the process. So 1 to 2 we know that it is a constant entropy process because S is constant, so 1 goes to Z, so 1 goes to Z, and we have these two options available. And in the second process, 2 to 3, it could be constant volume or constant pressure, and we can see 3 to 1 is again another constant volume or constant pressure. Among 2 to 3 and 3 to 1, 2 to 3 has a higher slope than the 3 to 1 process, so that means 2 to 3 should be constant volume and 3 to 1 should be constant pressure. So that way 2 is Y, constant pressure, and 3 is X. So option C is correct. Next problem, choose the correct statement. Processes spontaneously occur only in such a direction that the total entropy of the system plus surrounding increases and it is not decreases. Next problem, the latent heat of fusion of water at 0 degrees Celsius is 335 kilojoule per Kelvin, kilojoule per kilogram. How much does the entropy of 1 kg of ice change as it melts into water in each of the following ways? heat is supplied reversibly in a mixture of ice and water at 0 degrees Celsius, and option in the second condition, a mixture of ice and water at 0 degrees Celsius is stirred by a paddle wheel. So as ice melts into water, we have to find the change in entropy. So delta S for water at state 1, or for the case A, we can write it as summation of del Q by T. Del Q here is 335 kilojoule per Kelvin, and we are using only one mass of ice, so it can be 335 kilojoules. And the temperature at which the heat transfer is happens is at 0 degrees Celsius or 273 Kelvin. So this is 1.227 kilojoule per Kelvin. And now for the second case also we will have the same thing, so there is no change in any of this. So we will write water for the case B is 1.227 kilojoule per, the same thing goes. Now but what will be the difference for these two cases? When you have the total change in entropy for the case A, the heat is supplied reversibly to a mixture of ice and water at 0 degrees Celsius. So that means we had an 1 kg water mixture at 0 degrees Celsius, and this has converted from ice to water, and there is another body which can be very large, and the temperature difference or these things can be neglected, and there is some heat transfer which occurs reversibly over it. So heat from the other body comes to this, so that it becomes water from the reservoir or the source at 0 degrees Celsius. So now this is also losing some heat, that is 335 kilojoules, and this is a system, and this is also gaining heat of the same amount, and both are at the same temperature. So if you write this for the case A, the entire entropy generation is given by delta summation of delta Q by T, and this would be 335 by 273. So or I would write delta Q of the source by T of the source plus delta Q of the water by T temperature of this system or the water, and again it will be 335 by 273, which is generated by the which is given out by the source, so it should be negative, and plus 335 by 273 for the system or the water body, 1 kg water body. So now at the end it becomes 0. So there is no entropy increase or decrease in this process when it is reversibly the heat is transferred from another body at the same temperature. Now in case of the second case or the case B, there is no another source where there is a negative entropy which we had in the first case with the source. Now there is only work transfer that doesn't come under this entropy generation, so we will end up with only this Q delta QW by TW, and that is 335 by 273, which is 1.227 kilojoules. So what it essentially says is, when we have when we use some work to raise the heat or add heat to a system like this, we end up in generating entropy. But when we have an heat transfer from a source to a sink, there will be considerably less entropy in that process. And so here, since the source was at 0 degree Celsius, we had 0 entropy difference. But when it was assumed that it had been at a different higher temperature, then we will see the entropy getting generated. Next problem. 2 kg of water at 80 degrees Celsius are mixed adiabatically with 3 kg of water at 30 degrees Celsius in a constant pressure process of 1 atmosphere. Find the increase in the entropy of the total mass of water due to the mixing process. Cp of water is 4.187 kJ per kg Kelvin. So M1, so there is 2 streams coming in. Actually there is no flow, so you can say M1 at 2 kg of water. This is first, that is at 80 degrees Celsius, and the second body where 3 kg of water at 30 degrees Celsius can be found. Now these are mixed adiabatically, and we need to find the increase in entropy of total mass of water. So now using the first law equation, we can find the final temperature of the water. That is by using law of conservation of energy, we can find it. So at the third state is the mixture of both the things, and that will be 2 kg plus 3 kg, and that will be some 5 kg, and it will be at a final temperature of Tf. Now we can equate the enthalpy of the energy of 3 is equal to energy of 1 plus energy of 2. That is mcp mctf is equal to, so this can be m3 is equal to m1 c t1 plus m1 c t2. Here m3 is equal to m1 plus m2, and this can be written Tf is equal to C can be cancelled, and we will have m1 t1 plus m2 t2 divided by m3, or this is m1 plus m2. So this is 2 into temperature is 80 degrees Celsius plus 3 into 30 degrees Celsius divided by 2 plus 2, that is 5. So this, you can find the final temperature. That will be 50 degrees Celsius. So this is the final temperature. Now we can calculate the temperature. So entropy generated by the first body, which is around 2 kg of water, can be written as mc into ln of t2 by t1. So here m is 2 kg, c is 4.187, ln of t2 is 50 kg, 50 degrees Celsius, and that will be that will be 323 Kelvin, and similarly this will be 303 Kelvin, and this is 353 Kelvin. So we will have T2 by, T3 by T1, that is 323 by 353. So that will be minus 0.7437 kilojoule per Kelvin. And similarly for the second state, it will be M1 was here, so 2C ln T3 by T4, and this is 3 into 4.187 ln of 323 by 303. And this is 0.8029 kilojoule per Kelvin. So now total entropy generation is delta S1 plus delta S2, that will be minus 0.7437 plus 0.8029. And this will be 0.0592 kilojoule per Kelvin. Let's be back in our So in this problem, steam at 7 megapascal and 450 degrees Celsius is throttled in a valve to a pressure of 3 megapascal during a steady flow process. During this, determine the entropy generated during this process and check if the increase of entropy principle is satisfied. So, so there is a steam at 7 megapascal and 450 degrees Celsius initially, and this is throttled using a valve, and then the exit of the valve is maintained at 3 megapascal. Now, so this can be taken as state 1 and this is state 2. We know P1 is 7 megapascal, T1 is 450 degrees Celsius, P2 is equal to 3 megapascal. And since it is throttled, we know H1 is equal to H2. Now we can calculate the entropy for both the states. S1 is 7 megapascal and 450 degrees Celsius. So 7 megapascal is between these two, and 450 degrees Celsius is not here. That means the saturation temperature for 7 megapascal is only 250 degrees Celsius. Between 275 and 295, so it should be 285 degrees Celsius for 7 megapascal. But at the state 1, the steam is at 450 degrees Celsius, so that means it is a superheated steam. So going to the superheated steam table, we have 7 megapascal and temperature of 450 degrees Celsius. So this is the line we are interested in. We can find the enthalpy, that is 3288.3. And entropy is 6.635. So now for the second state, we know pressure, that is 3 megapascal, and the enthalpy is same as enthalpy at state 1, that is 3288.3 kJ per Kelvin or kg Kelvin. So looking at the 3 megapascal superheated steam, so here it is. Our enthalpy was 3288, so that is 3288 is between these two. So with this we can calculate the temperature and then calculate the entropy. At 400 degrees Celsius, the enthalpy is 3231.7, and at 450 degrees Celsius it is 3344.8. So now we need to calculate for 3288.3. So we can write straight line equation y2 y minus y1 y minus y1 by y2 minus y1 is x minus x1 by x2 minus x1. So here we can assume y as enthalpy, y as temperature. So then we will have T minus y1 is 400 divided by 450 minus 400 is equal to x is enthalpy, and the required x is 3288.3 minus 3231.7 divided by 3344.8 minus 3231.7. So temperature is 400 plus 50 into plus 100. Can you find this value?
Sir, it is 399 Kelvin.
399 Kelvin or degree Celsius?
Initially, what we
Yeah, this is degree Celsius.
degree Celsius.
Yeah, but it should be between 400 and 450.
So it's 425, sir.
425 Kelvin. So this is almost at the midpoint of these two. So then we can calculate the entropy. So similarly for entropy, we have temperature and entropy 400, 450. We know entropy at 400 is 6.923. 6.923, and similarly at 450 is 7.086. This is 7.086. So now we can do this interpolation, but we also know it is almost a midpoint, 425. So S2 can be set as the average of these two. So 6.923 plus 7.086 by 2. Calculate this.
Sir, it's coming out 7, sir.
7 kilojoule per kg Kelvin. So this is S2. So change in entropy is S2 minus S1. This is around 7 minus S1 is here 6.635. So we have 6.635. So we will find this.
Like 0.6695.
Negative 0.6. This is 6.6.
Yes, sir, 0.365.
Yeah, okay. So now we can see while throttling. So here the steam was throttled from 7 megapascal, 450 degrees Celsius to 3 megapascal. So now during this process we know only the enthalpy of the inlet and outlet is same. So we have taken that H1 is equal to H2, and then we found what is the entropy for the state 1 and 2, and we can see that the state 2 entropy has increased by 0.365 compared to the initial case. So if you do not have any questions, I can move on to the next problem. In the next problem, we have a 50 kg block of iron casting at 500 Kelvin is thrown into a large lake that is at temperature of 285 Kelvin. The iron block eventually reaches the thermal equilibrium with the lake water, assuming an average specific heat of 0.45 kilojoule per kg Kelvin for the iron. Determine the entropy change of the iron block. So this is first part of the problem, and second part is to find the entropy change of the lake water, and third is to find the entropy generated during the entire process. So entropy change, to find the entropy change of the iron block, we have T220. So this is MC dt by t. So this will be finally MC into ln of t2 by t1. So M is 50 kg and C of the block is 0.45, and ln of final temperature of the iron block will be 285, and initially it will be 500 Kelvin. we calculate the entropy change.
Sir, it is minus 12.64.
So this is minus 12.6
Kelvin.
kilojoules per kg. And now we can find the entropy change for the lake, and that is delta Q by T. So here for the iron case the temperature was constantly varying, so that is why we had to integrate and had ln of final temperature by initial temperature. But for the lake the temperature will be constant, so we can directly put delta Q by T. So now we need to find delta Q, and that is mc into delta T. So that means energy or the heat energy taken away from the iron block will be transferred to the lake. So now we need to find the mcp delta T of the iron block. That is again 50 kg into 0.45 SSMT value, and then delta T is from 500 Kelvin to 285. Can you calculate this?
So it is 4837.5. 9.67.
Sorry, sir, it is not 500, it is 285. The lake temperature is 285.
So 16.97.
16.97 So now the entropy generation is the summation of the both entropies plus entropy of the lake. So it is minus 12.64 plus 16.97.
4.33, sir.
4 point. Do you have any doubts in this problem?
Yes, sir.
Yeah.
Sir, before and after, is entropy increase or decrease, sir? Is increase, no, sir, always?
The entire for the universe the entropy will increase, but for any particular process the entropy can decrease. For example, here the iron block was at 500 Kelvin, and if you look at only the iron block, after it has put in the lake, it has cooled down. So from 500 Kelvin the temperature has come down. So as far as the iron block alone is considered, the entropy is decreasing, right? But the lake entropy has increased because of the heat transfer from the iron block to the lake. In total, the total entropy will keep increasing for real cases. But for an individual block, the entropy can decrease. Individual process and the individual mass or system.
Okay. Sir, minus indicate what, sir, in entropy, sir?
Sorry, minus.
Minus indicate what, sir? Entropy, sir.
Sorry, minus indicates the entropy has come down for the system. I couldn't hear you properly. So negative indicates that so this ion is S2 minus S1 or S final minus S initial, right? So final entropy of the iron block is lesser than the initial entropy, because it has transferred its
Okay, sir.
entropy to the surrounding or the lake in this case.
Sir, what is the initial of this lake, sir? Yeah, it is 16.97, sir. Or it is final, sir?
No, no, no. This is change in entropy. Change in entropy of the lake is only 16.9.
Okay.
Yeah.
We are not calculating absolute.
Yeah, yeah. We entropy, we can only define the change in entropy for any system, right? So we will only deal with change in entropy.
So by seeing delta as, how we are telling that the interval is decreasing, sir?
If it is negative, it is decreasing. So delta S is final entropy minus initial entropy. No, so if it is decreasing, if it is negative, that means it is decreasing. If it is positive, it is increasing.
Okay, sir. Now, sir, in case of lake, sir,
Hmm.
we are having positive.
Yeah.
So it may be negative in initial state.
You mean entropy of the lake initially?
Yes, sir.
Uh, no, see, entropy as such we cannot say. Only change in entropy can be defined, right? And if you go for a steam table, there will be some entropy values, but we will be only dealing with the change in entropy. So the absolute entropy value will not be used anywhere. And if at
Okay,
all,
sir.
so this is concerned about the classical thermodynamics, and there is something called statistical thermodynamics, right?
Right, sir.
Statistical thermodynamics, where they deal with the atoms individually. Like we consider the pressure and temperature as a whole unit, right? They will consider the individual atoms energy, the kinetic energy of the individual atom, rotational energy, and so on. So in that case, they find the entropy by using some probability of occurring at different states. So that is,
Nothing but microscopic thermodynamics.
yeah, yeah, microscopic, and this is macroscopic. So it can also be called as, this is macroscopic, can be called as classical thermodynamics, and microscopic as statistical thermodynamics. So
Okay,
there,
sir. Understood.
yeah. Coming to the next problem.
Sir, in the previous plan, what is the total entropy of the processor?
So in the total entropy, we have found that it is increased by 4.33. Total entropy of the lake plus the iron block has increased by 4.33.
Okay, sir. Okay, sir.
The next problem, hypothetical device is supplied with 2 kilogram per second of air at 4 bar and 300 Kelvin. Can you mute and unmute only when you want to talk, because noise is high, sorry. Um, Two separate streams of air leave the device as shown in figure below. There is no figure, sorry. Each stream is at an ambient pressure of 1 bar, and the mass flow rate is the same for both the streams. One of the exit stream is said to be at 330 Kelvin, while the other is at 270 Kelvin. The ambient temperature is at 300 Kelvin. Determine whether such a device is possible. So we have a device which where air at 4 bar and 300 Kelvin is supplied, and it comes out as two streams where it will be at 1 atmospheric pressure, 1 bar of pressure, and one stream will have a temperature of 330 Kelvin and the other stream will have 270 Kelvin. So we need to find if such a device is possible or not. And it is said that, so here the mass flow rate at the entry is 2 kg per second, and at the exit it is the same for both, so it should be 1 kg per second and 1 kg per second. So I will consider this as state 1, this is state 2 and 3. So we can calculate the entropy generation for this entire system. So the rate of entropy generation is given by mass flow rate m dot 2 s dot 2 plus m dot 1 s dot plus 1 minus m dot this is 3 m1 is 1. So here we know m1 is m2 plus m3. So this can be written as m dot 2 into s2 minus s1 plus m dot 3 s3 minus s1. So this is like so change in entropy or change in entropy can be written as for a compressible fluid gas or ideal gas Cp into ln T2 by T1 plus minus ln P2 by T1. So S2 minus S1 is Cp for the air is 1.005 kJ per kg Kelvin into ln of T2 by T1. So T2 here is 330 Kelvin, 330 by inlet temperature of 300 Kelvin minus R is 0.287 into ln of the final pressure is 1 bar and initial pressure was 4 bar. So can you compute this?
Is it 2.96?
Sorry,
96.
2.96. I am getting 0.4936.
Sir, it's 0.654 coming, sir.
0.65. You can start by steps. So this is 1.005 30 by 300 is 1.1, right? Minus 0.287 So here ln of 1.1 is, so this is 1.005 into 0.0953 minus 0.287 into 0.25, sorry, ln 0.25. it is minus 1.386. This is 0.3978. It comes to be 0.49357. Are you getting this?
Yes, sir. Same, sir.
Similarly, S3 minus S1 can be computed as 1.005 ln of T2 by T, T3 by T1, that would be 330, 270. So the third steam is 270, is at 270 Kelvin. So it is 270 by 300 Kelvin minus 0.287. The pressure is same for both the streams, so it is the same. One before. Can you calculate this?
So it is 0.291 kilojoule per kg Kelvin.
Kilojoule per. Now we have for the S generation, entropy generation, we have 2 into S2 minus S1 plus m dot 3 into S3 minus S1. So m dot 2 is 1 kg, both are 1 kg per second. So this would be 1 into 0.49357 plus 1 into 0.295. Calculate this.
So it is 0.78.
0.78 kilojoule per. So now because we have used mass flow rate, so this is kilowatt. So we can see the entropy generation is possible, so we can say that such device is possible to us. So a device wherein 2k some mass of air at high pressure 4 bar and 300 Kelvin is taken in, and at the exit there are two hot and cold exit. At hot exit the temperature is 330 and cold exit it is 270 Kelvin. So you can see such devices can, based on the second law of thermodynamics using the entropy principles, we have found such devices possible.
Sir, at the starting, sir, what kind of the equation we are using, sir?
This one.
M2 plus.
Yeah, so here I am taking the, say I am taking a box like this and I am seeing what is the entropy coming in and entropy going out. So for finding the entropy that I have generated, so whatever coming out of the box is the entropy that is generated by the box, right? By the control volume.
Yes, sir.
Yeah, so those terms will be positive and that will be m2 into s2 and m3 s3. And similarly, but I am taking some entropy inside and that is I am taking a negative sign, minus m1 s2.
So, yes, sir, minus M1 S1, sir. Why, sir? From where we are taking, sir?
Because so for this box I have one state coming in, two fluids, two stream going out. So for this control volume, it is consuming some entropy and releasing some entropy. So to find the overall entropy generated, whatever it is giving out will be positive, whatever it has taken in will be negative, right?
Okay, sir. Understood, sir.
So in this case, if the entropy generation is negative, that means it is observing say 8 kilojoule per Kelvin of entropy inside and only giving out 6 kilojoule per Kelvin of entropy, then that means such a device is not possible. But we have found that with the entropy generation is positive, so that means this device is possible.
Sir, this final answer 0.78 is kilowatt by
Kelvin, yes,
Kelvin, sir.
yes, yes.
How we are taking,
Okay.
sir, this?
So here with this S3 minus S1, we had kilojoule per kilogram Kelvin, right? So now we multiply with mass. That is mass flow rate. So that is M3 into S3 minus S1. So this has become kilogram per second into kilojoule per kilogram Kelvin. So here kg will go off. Then I will have kilojoule per second Kelvin. Right. So kilojoule per second is kilowatt per Kelvin.
Right, sir. Understood, sir.
So this is the rate at which the entropy is generated. Next problem. A room is maintained at 27 degrees Celsius while the surroundings are at 2 degrees Celsius. The temperature of the inner and outer surface of the wall K is equal to 0.71 watt per meter Kelvin are measured to be 21 degrees Celsius and 6 degrees Celsius respectively. Heat flows steadily through the wall 5 meter and 7 meter in cross section and 0.32 meter in thickness. Determine the rate of the heat transfer through the wall, the rate of entropy generation in the wall, and the rate of total entropy generation with this heat transfer process. So we have a wall. And this is say inside of the room, and this is atmosphere, and room is maintained at 27 degrees Celsius and atmosphere has a temperature of 2 degrees Celsius. The surface of the walls are at different temperatures. So inner surface is at 21 degrees Celsius and outer surface is at 6 degrees Celsius. So K is also given. K is 0.71 watt per meter and area is also given as 5 into 7, so that will be 35 into K. And delta X or the thickness of the wall is 0.32 meter. Now we need to find the rate of heat transfer through the wall. So that is simple, that is Q is equal to minus Ka delta T by delta X. So K is 0.71, area of the cross section is 35 into delta T is total heat transfer rate. So that is from the between 27 and 7. So we have 27 minus 2 divided by delta X is we should look into the wall temperatures. So that is 21 and 6. 21 and 6 by delta X is
Sir, we don't need to convert the temperature in Kelvin, sir.
here we have only change in temperature, right? So if I have to write in Kelvin, I will write 21 plus 273 minus 6 plus 273. Right. So now 273 will go off, then again I will have Pradeev minus 6. So when you write change in temperature, degree Celsius and degree Kelvin will be in the same.
Right, sir. Understood, sir.
So can you find the heat transfer rate?
That is 1164.84
Yeah.
watts.
So now you know the entropy equation. So whatever entropy differences that we find from delta Q by T will be same as the entropy generated for the wall. So this is 0 equal to some heat is entering the wall at 21 degrees Celsius. So that is uh, 294 Kelvin. So this is 294 Kelvin, and at the other side it is 279 Kelvin. So writing the summation of the heat transfer across the wall, we will have the heat transfer by temperature. So this is 1164.84, that is the heat transferred inside the wall to the wall, divided by the temperature at which it is transferred, that is 294 Kelvin. Similarly, the heat lost by the wall is again 1164.84, so we have negative for that. So this is 1164.84 divided by the temperature at which it lost heat is 279 Kelvin. So plus S gen is the entropy generated by the wall. So now we can write S gen of the wall. This is the rate at which it is generating. Can you find this?
So it is minus 0.213.
It should be positive 0.2, because we have 294 and 279. So when we write S gen, it will be interchange, right? Due to 279, is it fine?
This is 0.213, sir. Sir, in the problem, we are not taking minus sign, sir, in Fourier's law, sir.
Yeah, I am just taking the magnitude of the heat transfer. So we can, if you want to find the direction of the at which the heat is transferred, it will be different than the direction of the gradient. That is for, as far as Q is concerned, we are only asked to find the rate of heat transfer. Right?
Okay, sir. Sir, at the LHS, sir, why we are taking 0, sir? Entropy of delta changing summation of Q by T.
This is the equation we would have derived, right? So in the summation of Q by T plus entropy generated will be 0. we would write cyclic integral q by t is less than or equal to 0, right? So here this can be written as summation of q by t is less than or equal to 0. So summation of q by t uh, plus entropy generated will be minus of some value can be equal to 0. So if you take this, you will have minus entropy generated. So this means a negative value, right? Less than or equal to 0 is a negative value. So that is equal to the magnitude of the entropy that is generated.
Okay, sir. Understood, sir.
Okay. So next is total entropy generated. Is q by so this is 1164.84 divided by the temperature of the atmosphere is 275 minus 1164.84 divided by temperature of the room, that is 27 degrees Celsius and 300 Kelvin. Can you find this?
So it's coming as minus 34.59.
Minus 30, minus 34.9.
Yes, sir.
I'm getting 0.353.
Sure. Yes, sir. 0.35. That 3.29. I forgot 1 0.
Okay. So this is clear. We can move on to the next problem.
Sir, the last, sir, what we done, sir?
So here, similar to the last this case, we had 0 is equal to summation of q by t plus entropy generation, right? So entropy generation is minus of delta qt. So that is q by temperature of the atmosphere. What will be? here, that is why we have positive here, and atmosphere is gaining, so we are fine with it. We don't see
Sir, for the atmosphere, taking negative, sir.
yeah, atmosphere is losing heat or gaining heat. So it is similar to what we had in the wall case. So here we had 279. The body at 279 is losing heat. Or I think so total entropy generation is equal to entropy generated by the uh, room, entropy change of the room plus entropy change of the atmosphere. So for the room, room is maintained at 27 degrees Celsius and it is losing heat, so it is it will have a negative negative heat transfer, and at a temperature of T room. And for the atmosphere, it is gaining heat, so it is positive Q by T atmosphere, and that is what we have got here.
Okay, sir.
This is similar to the previous cases. So as far as the wall is considered, only the wall is considered. It is Okay, anyway, I will get to this in the next class. But entropy generation should be always positive, but why we write like this and here it is like this, I will get in the next class. Okay, in the next problem we have a Carnot cycle where a heat is supplied at 350 degrees Celsius and rejected at 27 degrees Celsius. The working fluid is water, which while receiving heat, evaporates from the liquid at 350 degrees Celsius to steam at 350 degrees Celsius. The associated entropy change is 1.44 kJ per kg Kelvin. If the cycle operates on a stationary mass of 1 kg of water, how much is the work done per cycle and how much is the heat supply? If the cycle operates in a steady flow with a power output of 20 kilowatt, what is the steam flow rate? So we have 1 kg of water totally available, and there is some Carnot cycle running. So in the TS diagram, Carnot cycle can be represented as a rectangle. The higher temperature is 350 degrees Celsius and lower temperature is 27 degrees Celsius. So we can convert this to Kelvin scale. This will be 623 Kelvin and this will be 300 Kelvin. And it is while heating, the entropy change is given as 1.44 kilojoule per kilogram Kelvin. So now we can calculate the Qin, that is temperature into delta S. So temperature is 623 Kelvin and delta S is 1.44 kilojoule per kg Kelvin. So we calculate Qin.
So it is 897.12 watts.
897.12 kilojoule per kilogram, and we can calculate the efficiency of the Carnot cycle. So that is 1 minus low temperature reservoir by high temperature reservoir, that is 1 minus 300 by 623. Can you calculate the efficiency?
So it is 51, sir. 51.8%.
Okay. And similarly, work output can be calculated as efficiency into heat input, that is 0.97.
So it is 457.8 joule,
457
kilojoule.
kilojoule per Kelvin. So we have calculated the work output and the heat input. Next is to find what will be the power output. Power output is given as at the rate of 20 kilowatt. We need to find the steam flow. So now this power output we can write it as mass flow rate into work done per cycle, or work done by per kilogram of mass. So we can calculate m dot as W dot by W, and W dot is 20 kilowatt, that is 20 divided by the specific work output is 457.8 kilojoule per kg. So finally we will get kg per second. Can you calculate the m dot?
Sir, point 043
0.043 kilogram per second.
kg.
Any questions?
Sir, from the question, sir, the associated entropy change, sir, can you explain from that on that point, sir?
Sorry, entropy change.
Yes, sir. From the associated entropy change, can you explain from that, sir? Question, sir.
Question. Okay. The associated entropy change is given as 1.44 kJ per kg. So that is while receiving heat, the working fluid is water, which receives
Water.
heat, evaporates from liquid at 350 degrees Celsius to 350 degrees Celsius T. So while heating, the temperature is constant, and they have given what is the entropy change associated. So that is this point to this point. Is given.
Sir, while heating, evaporates from liquid at 350 to 350 degrees Celsius to steam at 350. So we are heating water and converted to steam.
Yes, yes.
So the both having same temperature, sir.
Yeah, yeah. So during latent heat of vaporization, we have same temperature, no?
Oh, okay,
Within the vapor.
okay. Okay, sir.
Okay. Next problem. So I will just close. Heat engine receives reversibly 420 kilojoule per cycle of heat from a source at 327 degrees Celsius and rejects heat reversibly to sink at 27 degrees Celsius. There are no other heat transfers for each of the three hypothetical amounts of heat ejected in A, B and C. Below compute the cyclic integral of dq by t. From these results show which case is reversible, which is irreversible, reversible, and which is impossible. So heat engine receives a heat, say Q in is 420 kilojoules, and at a temperature of high temperature reservoir of 327 degrees Celsius, and we can calculate the, it will be 600 Kelvin. Similarly, the low temperature reservoir is at 27 degrees Celsius, and that is 300 Kelvin. Now we need to find the, and for EA, the Q out, or so I will write this as QH and this is QL. QL is given as 210 kilojoules or 105 kilojoules and 315 kilojoules. So these are given. We need to find which process is reversible, irreversible, and impossible. So now we can find the cyclic integral of dq by t, and that will be, for the first case, we have 400, and so we have qh by th minus ql by tl. So qh is 420 by TH is 600 minus QL is for the first case it is given as 210 by TL is 300. So can you calculate this?
So it's coming 0, sir.
0. So now this means it is a reversible cycle, and for a reversible cycle, when the heat from the high temperature source, we have a heat engine, this is at 600 Kelvin, and this is at 300 and some work output is taken. So when so this is at 420 kilojoules, and when the heat rejected to the low temperature reservoir is 210 kilojoules, we find that the entropy generated is 0. So that means this is reversible process, right? Now for the other cases we can say any heat rejection less than this is not possible, right? Any heat rejection less than this will mean that work output is more than the reversible case. So now we can say reversible work output is 210 kilojoules, and any calculation which says the work output is more than this will mean that that process is not possible, right? So now and that means any heat rejected to the low temperature reservoir less than 210 is not possible. So now we can see B option is 105, so that means it is less than 210, so we know that it is impossible. We can also again calculate all this and find, then we will end up with having some positive value. So we know del Q by, so here the dq by T we can calculate it. I think this is also part of the problem, we have to complete this. So 420 by 600 minus 105 by 300.
That is 0.35.
0.35, yeah. So this is positive. We know del Q by T should be negative. Should be less than or equal to 0 for any case, right? If it is 0, it is ideal or reversible case. If it is less than 0, it is possible case. Here it is greater than 0, so we know it is impossible. Similarly, in the third case, the Q L is 350, so we can find the Q by T, which will be 420 by 600 minus 315 by.
So it's coming minus 0.35.
Yeah, minus 0.35 kilojoules Kelvin. So here the cyclic integral is less than or equal to 0, so that means this process is possible, and it is irreversible because it is not 0.
Yes, sir. Sir, what would be the work done for these cases, sir?
We can calculate work done. So here work
So it's
output.
always less than 210.
Sorry.
It's always less than 210, which is getting in case 1.
Case 1 is 210, so that is work output is also 210. Heat rejected to the low temperature reservoir is also 210.
Yes, sir. So it's other cases is always less than 210.
Other cases means in impossible case we will get something more than 210, so that is not possible. For the B case, we will get work output as 420 minus 105, that will be 315, right?
Right, sir.
Yeah, that is not possible because it is more than the ideal case itself. But for third case, option for the C thing, we will have 420 minus 314. That will be 105. Yeah, 105. So this is less than the ideal work output, so this is possible.
Okay, sir. Sir, each and every problem, sir, we are concerned with the entropy, sir,
Yeah, yeah.
for devices existing or not,
Hmm.
for the cast block.
Yes, yes.
So we are not considering that device is existing or not. What it should be the efficiency it work done. Just calculate entropy, and we can say that device is existing or not.
Yes.
But all parameters are not that on that much level.
All parameter means.
Like work done. Take example for that device, sir. We are just calculating entropy and
Hmm.
uh, telling this existing or not.
Yeah. So, as per the second law, for a process to occur, the entire entropy should keep on increasing, right? So, we are going by that law. If a proposal for some device is there, we find what is the entropy generated during by the device. If it is positive, we can say that this is theoretically this device is theoretically possible.
Okay, sir. Just defining the entropy, we can accept that.
Yes, yes, yeah. So, for example, this is one problem where you will find. Yeah, this is one problem where a dealer advertises that he just received a shipment of an electrical resistor heaters for residential buildings that have an efficiency of 100%. And assuming an indoor temperature of 21 degrees Celsius and outdoor temperature of 10 degrees Celsius, determine the second law efficiency of these heaters. So that means heater is there for a home, and he says that this heater is 100% efficient as per the electrical terms. But we know we can run a refrigeration or a heat pump which can supply which can take heat from the surrounding and pump the heat into the room to make it warm. And for this there should be some work input that has to be given, right? So in this case, in a heater case, if the heater needs 100 joules of heat input to be supplied to the room, then we will spend 100 joules of electrical energy. But in case of this heat pump, we can supply say 10 joules of energy, and the pumping will be it can take in, so this we will give only 10 joules of energy. It can take some 50 joules of energy from the atmosphere and then give into like 60 joules in total. So that is a advantage of having a heat pump over a simple resistor. But obviously the initial cost will be high and all, but operation wise it is much cheaper. And so for this we can calculate the COP. So we would have calculated the COP of the heat pump, right?
Sir, that 50 joules coming from atmosphere, sir.
Yes, yes. So we take heat from the low temperature to high and pump it to high temperature.
Atmosphere, for example, sir.
Atmosphere here it is Outdoor temperature is 10 degrees Celsius, 10 degrees Celsius, and here it is 21 degrees Celsius. So this is 283 Kelvin, and this is 273 to 94 Kelvin.
Sir, can you explain that again, sir? Not understood, sir.
So we can run a heat pump and there are two thermal reservoirs, so low thermal reservoir and high thermal reservoir. So this is at say 283 Kelvin and this is at 294 Kelvin or 10 degrees Celsius and 21 degrees Celsius. Now we can run a heat pump by supplying a work input, and then this can pump some heat energy to the room. So if you are pumping, say you have some energy Q into the heat pump, or I will say QL, and this is QH. So by heat balance you will say QH is equal to W plus QL, right? This is what is happening in the refrigeration or the AC and the fridge also. We supply, so here for a refrigerator, our aim is to take out heat from the low temperature reservoir, that is QL, and by supplying some energy, and that is QW. So this is called a coefficient of performance of a refrigerator or a heat refrigerator in this case. And for a heat pump, our aim is to pump heat to the high temperature reservoir. So there the COP is QH by W.
Understood, sir.
Yeah,
Understood, sir.
you are able to understand this, right? So now for theoretical or when we have a reversible heat pump, we can calculate what is the COP just by using the temperatures. So for COP of the heat pump is QH by W, or this can be written as QH by QH minus QA, right? When there is no entropy generation, or when you use a reversible heat pump, this can be written as TH by TH minus TA, and TH is 294 Kelvin, and in the denominator it is 294 minus 283. Can you calculate the COP?
Size 26.72.
26.72. So this means when I supply only 1 joule of work input, I will get so I will not get 60 joules like I said, I assumed earlier. I will be getting 26.7 joules of heat energy inside the room, and this will be 25.7. Can you understand this?
Yes, sir.
Yeah.
But this COP we are taking, sir, as a 26.7 joule, sir.
No. This don't have any unit. This is like a efficiency. So in efficiency, sorry.
You are right, sir. J na, sir. You are right. 26.7 joule na, sir.
Yeah. So here I assumed 1 joule of work is given in. So QH by W, no. So if I give 1 joule of work input to the heat pump, it will pump in 26.7 joules of heat energy.
Right, sir.
And similarly, if you consider the COP of the refrigerator, here it will be, you would have found the relation somewhere. COP of the refrigerator is COP of the heat pump minus 1. So here it will be 26.7 minus 1, that is 25.7. So now if I supply only 1000 watts of energy to the refrigerator, it will take 25.7 1 kilowatt work input to taking 25 kilowatt of temperature from the low temperature reservoir and pump it to the high temperature reservoir. So now we can see this is more efficient than the resistor that we have already had. So now in this case we found the COP of the refrigerator is around 25.7, but in reality you can find the COP is around 3 to 4 or something. This is only a theoretical value, like when we use a reversible refrigerator, but in actual we have many losses. So finally the COP of the refrigerator will be around 3 to 4 that we use in our offices. And now we have been told to ask the second law of efficiency of these heaters. So that means second law of efficiency is actual efficiency by reversible efficiency, or here it can be COP actual by COP reversible. So COP actual for the heater is only 1, because for every 1 kilowatt of heat input it will supply 1 kilowatt heat to the room, and COP of the heat pump for a reversible case is 26.7. So we can calculate what is the second law of efficiency in percentage.
So it's coming 3.7, sir.
Yeah, 3.7% is the second law of efficiency of the heater, but the dealer claimed that it is 100% efficient, right? So these are like marketing gimmicks. Actually second law of efficiency will be much lesser, but they will say as per first law of efficiency it is 100.
Sir, why it is COP for actual is 1, sir?
COP of actual, that is the COP of the resistor, electrical resistor.
Achha. Okay, sir. Okay.
Water is heated at a constant pressure of 0.7 megapascal. The boiling point is 164.97 degrees Celsius. The initial temperature of water is 0 degrees Celsius. The latent heat of evaporation is 2066.3 kilojoule per kilogram. Find the increase in entropy of the water if the final state is steam. So that means if you want to plot this process in a TS diagram, initially the water is at 0 degrees Celsius and pressure is 0.7 megapascal, that is 7 bar. 7 bar and 0 degrees Celsius is will be a subcooled liquid. Why it is called subcooled liquid? Because at 7 bar the boiling point is the boiling point for at 7 bar will be more than 100 degrees Celsius, right? Even at 1 bar the boiling point is 100 degrees Celsius, and if you have a water at say 50 degrees Celsius, it is called subcooled liquid. Because it is cooled beyond the saturation temperature. Similarly for 7 bar it should be the boiling point is given as 164.97, around 165. So 165 will be somewhere here, and our first point is at 0 degree Celsius. And when you start heating at constant pressure, it will constant pressure of 7 bar, it will first reach the saturated dome line, and it will become liquid, saturated liquid, and then latent heat of evaporation is supplied, that is given as 2066.3 kilojoule, and say this is 0.3, and the water the final state of is given as steam. So that means the heating process ends at this point. So now we need to find the increase in entropy of the water. So this can be increase in entropy can be set as total increase in entropy can be split into two, for the process 1 to 2 and 2 to 3. For the process 1 to 2, we know the temperature keeps on changing as the heat is added. So we will have dq entropy, change in entropy can be given by integral dq by t. So this is mc into dt by t. Then we will have the ln terms. So so m is given, m is should be taken as 1, and c of the water we know that it is 4.187 kilojoule per kg Kelvin, and for the integrating this dt by t, we will have ln of final temperature by initial temperature. Here the final temperature is 165 or 164.97. No, we have to convert it to Kelvin scale. This is 437.97 Kelvin, and 0 degree Celsius we know it is 273 Kelvin. So here we will have ln of final temperature by initial temperature. Final is 437.97 divided by initial is 273. Can you calculate this?
Sir, it's coming out 1.97, sir.
1.97. And similarly, entropy change between 2 to 3. Here it is a constant temperature process, so we can directly write Q by T. So here Q is the latent heat of vaporization, that is given as 2066.3, and the temperature at which the heat transfer happens is 437.97 Kelvin. So can you calculate this entropy?
Sir, it is 4.71 kilojoule per kilogram Kelvin.
So total entropy generation is entropy generation plus 1.97 plus 4.7.
Sir, 6.68, sir.
6.68. Any questions?
Sir, this Q, sir, 2066 from.
Yeah, so it is given as the latent heat of evaporation is 2066.3 kilojoule per kilogram. So that will be from this part, from the point 2 to 3.
Okay, sir.
Problem, 200 meter cube of rigid tank contains compressed air at 1 megapascal and 300 Kelvin. Determine how much work can be obtained from this air if the environment conditions are 100 kilopascal and 300 Kelvin. So this is a problem where we need to find the availability of a given system. So availability is generally given by this expression, change in internal energy plus P naught minus into V minus V naught and so on. Here we can assume the kinetic energy and potential energy are zero, so these two terms will flow off, and the initial and final temperature are 300 Kelvin, so this term will also be cancelled. Now we need to
Initial
find, yeah,
internal energy, sir.
internal energy is CV into temperature, right? So temperature is constant between the initial and final, so we have that to be zero. Okay.
Okay, sir.
Now we can calculate the mass, which is given by PV by RT. Pressure is initially the pressure is 10 power 6 or 10 power 6 pascals into volume is 200 meter cube, divided by R is 287 for air, and the temperature is 300 Kelvin.
Sir, 2322, sir. 0.88.
Kilogram. Now we know availability is M into 5 R, and that is M into P naught V minus V naught minus P naught into S minus S. Here for V naught into V minus V naught, we know V naught value we know, but volume at the final state is not. So this can be written as RT1 by V1 minus RT1. So here R can be taken, RT1
Sir, in the question, V is given now, sir.
but V naught we don't know, right?
Yes, sir.
I think we can try to calculate V naught directly and then we know PV equal to MRT, so V naught will be V naught T. So here M is MRT naught by, so M is 2 3. I can approximate this to 2 3 2 287 into temperature is 300 Kelvin by pressure is 100 kilopascal. 100 into 10.
Sir, it's exact 2, sir.
2 meter cube.
2 meter cube.
Okay. So now we can S minus delta S is S minus S naught. It can be given as Cp into ln of P by T naught minus R into ln of P1 by P naught. So this we know it is 0. Water temperature are same, so ln 1 will be 0. we will end up with minus r into ln of 200 meters. So that also we can calculate. So that is minus 287 ln of initial pressure is 10 power 6 and final temperature pressure is 100 into 10 power 3. So we have ln of 10.
So 2960, sir. 0.4.
So is it minus 2960, right?
Yes, minus, sir.
2960.4 kilojoule, sorry, I think joule per kilogram. So now putting in this equation, we have mass is 2323 into P naught is 2 and volume is initial volume was 200 millicubic, right? 200 minus 2 minus temperature is 300 into delta S is we can say this is positive and this is 296. Can you calculate this? I think sorry this is pressure, right? P naught is 100 into 10 power 3.
So it is 4.8 10 power 10.
4.8 into 10 power 10.
So delta S, sir, can we take negative, sir, here?
No. Here this had a negative sign, no? Okay.
Okay, okay, sir. Okay.
See, for this delta S, I am getting 660.84. Can you check once?
not having that difference, sir. It's 4.6 into 10 power 10.
Hmm. Okay, actually the first term here it should be specific volume, only then we should multiply with mass, right? But here we already had the total volume, so this need not be multiplied with the mass, and only the enthalpy we had specific enthalpy, so this is multiplied with mass. So with this I am getting 480 plus this.
Where we have done changes, sir?
So in x1 here this p naught into delta v is there, no?
Yes, sir.
So this is if you have specific volume, then you will multiply with the term mass term. Here we had the total volume, no? 202.
Yes, sir.
Yeah, so we need not multiply with the mass for the pressure term, and only for the space entropy change we need to.
So that mass did not need to multiply the whole.
Yes. Mass is only for the entropy.
Mass is only for entropy.
Only for the entropy term, because for entropy we find specific entropy, no?
Yes, sir.
Yeah. So only for that we need to multiply.
The reason is only for there is a specific entropy.
Yes. Mass is only for specific.
So in previous problems, sir, I think we multiply with mass, na, sir.
No, for since it is specific entropy, we are multiplying with mass, so that it will become. So this term will become joule, right? We are multiplying with kilogram and Kelvin. But for the first term, we have pressure in pascals into volume. Volume is in meter cube. This is Newton per meter cube into meter square into meter cube. So then it will become Newton meter, that is joules for this case. Correct, no? Then we need not multiply with mass again for the pressure term.
But from the equation, we need clearly to multiply the both
Yeah,
for.
because in the equation here this is specific volume, meter cube per kilogram. All are specific values. But here we have already put the total volume. So this is also specific volume here. Or we can calculate the specific volume and multiply entirely. So then specific volume you have to again calculate 200 by 2323. This will be volume 1, specific volume 1, and specific volume at that state will be 2 by 2323. And then you will multiply again with that mass. No? That is why we have.
So, sir, delta S is also in specific, na, sir? Kg.
Yes.
So here we are multiplying with mass.
So to find the total energy, is equal to mass into specific energy, right?
Right, sir.
Yeah, so here we will have kilogram, and specific energy will be kilojoule or joule per kilogram. That is how we will get joules.
Joule.
Yeah, so now we are multiplying pressure into volume. Now pressure is meter cube. If you multiply pressure with specific volume, then we will have pressure as Newton per meter square, and volume will be meter cube per kilogram. Correct, no?
Right, sir.
This will be Newton meter per kilogram or joules per kilogram. So this is equivalent to a specific energy. To find the total energy, again we have to multiply with mass.
Right, sir. By the formula to the.
Yeah, but what we have substituted here is 200 meter cube and 2 meter cube. Just here, 200 meter cube and 2 meter cube. These are total volume, not the specific volume. Can
Yes,
you?
sir.
Yeah?
That is a that the volume is not a specific here. 200 minus
Ah,
2.
it is in meter cube, not meter cube per kilogram.
Okay, sir. Okay, sir.
Sorry if I am confused. Okay, any other questions?
Related to the problem, no, sir. The problem is clear, sir.
Okay, any general questions here?
Sir, in general questions, sir, what is the exact form of the thermodynamic first law, sir?
Energy is conserved, total energy is conserved, so you can write Q heat added to a system will be what temperature system plus change in internal temperature of the system.
So the circular integral of Q is equal to circular integral of QW.
This is for a cyclic process. So when a system is operating in a cycle, when you say in a TS diagram, we have some process. So then finally you can say the total work output from the cycle is equal to the total work input of the cycle.
So here there is no need of internal energy concept, sir.
Because when a system is undergoing a cycle, that means it is coming back to the initial state itself, right?
Yes,
So
sir.
from
Right,
1
sir.
it went to 2, 3, 4, 5, and then again came back to 1. So that means initial temperature or the initial internal energy is again it has come back. Even though through the process it has increased or decreased, whatever, finally it has come to the same internal energy.
Okay, sir.
That is
Okay.
how we can remove the delta U.
So, sir, this can be written as dou Q of any something path minus dou W of.
You mean partial derivative
Yes, sir. Partial derivative.
with respect to?
With respect to no, sir. For example, you are taking here example of TS diagram. So, partial derivative of Q at 1 to 2 minus
Okay.
partial derivative of 1 to 2 W is equal to some other part
Yes,
1
yes,
to
yes.
5, 1 to 3
Yeah,
like
here
this.
you can say Q1 to 2 plus Q2 to 3. Q5 to 1 is equal to same W1 to 2.
If you bring this work done LHS, then it's equal to the W delta U, sir.
Yeah, then now what will happen? You will have Q12 minus W122. I will write only three process, Q223 minus W223 plus Q321 minus W321. So this will be 0, right?
Delta U, sir. 0, sir. Delta U, sir.
No, I am writing from the cyclic integral term. I will now convert to
Okay.
delta U, okay? So now this is delta U 1 to 2 plus delta U plus delta U 2 to 3 plus delta U 3 to 1. This is 0. So I will just find what it is, okay? So now this is internal energy 2 minus internal energy 1 plus internal energy 3 minus internal energy 2 plus internal energy 1 minus internal energy 3. Now you see it will be 0. 2 and 2 get cancelled. 3 plus 3 minus.
Yes, sir. But what is these three laws are telling a common point, meeting at common point, or these three laws are one law in the three representation telling these three key points?
Which 3 law you mean to say?
Three three laws, no, sir. Three representation. We are
Thermodynamics first law, second law and third law.
no right. Not three laws, sir. We are writing first law in terms of three
In
representations.
3 forms, okay, yeah.
Yes. So they are meeting at a point, or they are
Like one
divergent.
common idea written for different conditions. So this can be said for one condition alone. This is for a cyclic process. So this is for a process. This is for a cycle.
Or this integral circular integral is for uh, open mass system, sir. Is like that.
No. These are for closed mass systems. Yeah, these are for closed mass. For open mass, you will have steady flow energy equation, right? So that is also first law for steady flow energy, steady flow process.
Okay, sir. Sir, by the what the sir thermodynamics. So it is a axiomatic science, or it is a heat we are taking work, or it is an interaction between heat and work, or it is a heat which is in dynamic flow.
You can go through the textbook. I think different people could tell a little differently. You can say heat and work dynamics between the heat and work energy.
So heat is in motion, we are taking work from that.
No, heat cannot. You cannot tell heat is in motion. You can say heat can transfer because only mass can be in motion. The interaction between
Yes, sir.
heat energy and work energy, mechanical energy.
Yes, sir. But some of the faculties they define that thermo means heat and dynamic means with
Motion.
something in
Yeah,
motion.
yeah.
So
So it is like getting heat moving from one place to another. It's like getting transferred from one point to another.
nothing but is transferring. The dynamic stands for transferring.
Transferring, yeah. Heat getting transferred to work or work to heat. Things like that.
Sir, that heat and work having same unit, sir.
Yeah, joules.
Yeah, so they are convertible each other. So,
No,
so
no,
the,
no.
that's
Only
why they are having. That's why they are having
no, no,
same
no,
unit or having other reasons, sir.
no. See, all energy will have the same unit joules, but heat only work energy. Work can be directly transferred to heat energy. So that is the second last stage. The opposite cannot be done completely. If you have 100 joules of sorry 100 joules of heat energy, you cannot convert 100 that to 100 joules of work.
Right, sir.
Yeah. Any other
So,
questions?
so reason for having same unit, sir?
Yeah, no, all energy will have same unit. See, kinetic energy, potential energy, everything will have the same unit. It is energy, no?
Yes, sir. It's energy. Okay,
Energy
sir.
can be of different forms. All form will have the same unit.
Sir, as a
Electrical
career path,
energy
sir.
also will have the same unit. Joules, watts,
Uh,
power.
okay, sir. Sir, as a career path, sir,
Hmm.
what is a blueprint for the thermal engineer, sir?
Means what you want to become or what do you mean by blueprint?
Blueprint means, sir, as a journal, sir, for a graduate to the higher studies,
Hmm.
what can be a blueprint, sir?
No, it depends upon what you are interested in and
For a thermal, sir, for a thermal.
yes, yes. So it depends upon what you are interested in. You are already master student, right?
No, sir, I am a graduate, sir, no masters.
Okay, undergraduate UG. So based on what your interest is, you should pursue your higher studies. If you are interested in thermal engineering, then you can do MTech in thermal, and then maybe if you are further interested in doing research, you can do research, or then join the job website or so on. So it's not like one solution for everyone. It only depends upon what you are interested in.
Okay, sir.
Okay.
Sir, so what are the next steps, sir? What can be a next step for a student, sir? As you are the PhD student.
Yeah. Like if you are interested in higher studies, you can go for it. Otherwise, if you are interested in looking for a job, you can go. Otherwise, what do I say? If you are interested in IES or things also, you can pursue. What is your interest?
Sir, my interest is taking higher studies, sir. But
Hmm.
while I'm reading these subjects, sir, it's like I'm reading thermal subjects. So I thought I must need to go to thermal.
Hmm.
While I reading design subjects, oh, this is a subject is very good. So I must need to go in the design. So
Okay.
while I'm reading applied science like
Hmm.
mechanics or like that.
Hmm. Everything you are interested in.
No, sir, but
Yeah, then
uh,
you can do 3 masters also, no problem.
is this a solution for this?
Yeah, yeah. What is there? What is wrong in doing 2 or 3 masters? If you are interested, you can do. But you can feel that you are more inclined towards one or the other. You should be able to find. Then, if you are able to find, then you can do masters in that thing first, and then maybe next, if you are further interested in doing research, you can do PhD.
Okay, sir, but what are the in higher studies?
Hmm.
Uh, what I am having options, sir? Is everybody knows, sir? Yes, after the mechanical engineering, you can go to the master. But what are the options, sir?
So, masters
For a
in
thermal, for a
IIT,
thermal.
most IITs you will have MTech in thermal engineering, design engineering, or manufacturing engineering.
Manufacturing and what, sir?
Manufacturing, design, and thermal.
Yes, sir. Yeah, this is a basic, but after the graduation, sir,
After
for
a
a thermal.
post graduation.
No, no, after graduation, sir.
No, you are currently doing bachelor's of engineering in mechanical engineering, right?
Yes, sir.
Yeah. So then after you will do post graduation, that is MTech or ME, that you
Yes,
will
sir.
be doing in thermal design or manufacturing. You want further, or after that, after masters, you want to know what is the option?
First, before masters, if you tell it better, sir. Before masters, sir, what I am having options, sir. Like before, after intermediate, I have a lot of options that taking degree, taking engineering, or going to the uh, some other fields. So after graduation, what in the thermal, what I have options, sir.
In thermal, like in institute like IIT, you will have only MTech in thermal engineering directly. Then after you join, you will have choices of having different courses. Like you can elect different course. If you are interested towards ice engine, you can take courses related to ice engine. If you are interested in refrigeration, you can take mini courses related to refrigeration, and then you can specialize on some particular topic.
So master in having only common course for all having common course.
Yeah, at least so far what I've seen, it is like this. In big IITs like IIT Madras, Bombay, Delhi, and all. At least when I was trying for admission, it was like that. Now also I think it should be the same.
Okay, sir. Sir,
Okay.
in which year you are studying in PhD, sir?
PhD I'm in third year.
Third year.
Okay, I think it's already half an hour past the time.
Yes, sir.
Yeah.
It's
So,
okay.
if you have any further questions, you can also mail me. Right?
Okay, sir. 1 second, sir. Okay, sir.
Yeah. Okay. Thank you.
Okay. Thank you. Thank you very much, sir.